Good evening mga ilagan. We will continue with our discussion design of structural members. So in the last video, we are done with roof truss and then floor truss and then beams and then columns and then some of the connectors. Now what's left are the wall studs and the diaphragm and shear wall. But before we proceed with Woolstead, I forgot about the vestibule framing. So we'll just start with the vestibule framing, wherein we will consider the snowdrift. And considering the snowdrift versus the possible panding load, there's a like I would say 99%, or on this in this case 100% that snowdrift will govern with regards to or versus the funding load. But as I mentioned before, you just have to make sure that if when you design for funding load, there is no like the if you have a lower roof, the rainwater leader is not discharging to the lower roof um to avoid like really heavy landing load. So on this one, we'll just assume that the downspout is discharged directly to the ground, not through the vestibule roof. So going back to the vestibule, so this is our plan. So we have 10 by or 20 by 15. So this is our, so for example, if this is our wall, right? And then we have the opening, which is this is 10 feet opening, and then we have our this is 15 feet, and then 20 feet. So it's not drawn to scale, but this is 15 feet, and then this is 20 feet. Therefore, this one, assuming this is in the middle, your opening, so this portion would be 5 feet and then 5 feet. Now, to frame the vestibule, like for the roof framing, you have at least two options. It's either you span your trusses in this direction, or if roof joist will work, then maybe roof joist, like PGI or 2 by 12. It depends. But assuming, man, the load is really heavy. Let me check how much was our. So our snowdrift is 130.3 and then down to 70.18. So this is our roof snowdrift. Um, so so this is I think it's 130.3. 130.3. So this is our snowdrift load this is 70.18 and then this is 130.3. So this is our snowdrift load. So it's either you frame it this way. Now the only downside with this one, if you attach the or if you support the trusses with a beam like this one, you will use this one as a support for your truss, then there's a bigger chance that this member will be really huge because imagine this is 130.3. So the only issue with this one here is um if you have if you cut section if you cut section like right here and then looking in that direction, we will draw below. So if you cut section, so this is your, oh, so this is your wall, and then you have your beam embedded here, right? You have your beam, and then it's either you will have your truss that sits on top of your beam. But the problem with this one is if you will have your truss sitting on top of your beam, then we will have issue with how to attach the I mean it can be done, but most of the time the truss manufacturer won't allow that one because that would be a problem on their part. So if you do it this way, then it means you will have your bottom plate here, and then that supports the upper roof. So and most likely the truss manufacturer won't allow that one. I mean, if you really force them to do that, then they have no options, but the members will be really huge. So another way of doing this one is you will have some kinds, if this is your beam, right? If this is your beam, then this is your wall. Sometimes we will use so if this is your truss, then we will use a truss hanger, like Simpson hanger here. So that's also fine. And then, like I said, this beam is already supporting the roof above, the upper roof. And then will support also the lower roof, the vestibule roof. That will be really a huge member. Now, another way of framing this one is instead of having this beam to support the roof, this one, what you can do is in the in the framing plan, instead of having this beam like the one inside, like inside the wall, you will run another separate beam here outside, and this will be supported by, because you have load bearing walls here, this one. So these are solid walls, this one also. So you will have a like a built-up post here, then built-up post on this side, and then you can run your beam. So if you look at the section, it would look like this one here. So if this is your wall, and then you have your beam, right? And then you will have another beam outside right here. So you can do that one. And then when you draw your cross section for left section of your truss, it will look like this one. So you will have your main, so this is your bottom chord, we have your top chord, and then your wave member, whatever the shape or the profile of your truss. And then right here, since you have your beam here, then you will have another member here, which is basically cut short to fit to flush the beam below that one. And then the truss manufacturer will just do a metal plate connector here. So that's another way of framing this one, and then you will have a beam. Now, the other way of framing this one is instead of using a beam right here below, you will have this entire, oh, you will have this entire depth, this one, and it will be a girder truss. So it can be a girder truss. And then again, if you look at the plan view, that girder truss will be supported by your what we call this one, your built-up post on that side. This way, your load on the uh, main building will be separate from your vestibule. And then this would result into a um, well, you have two beams, but it will be a shallower beam, and then maybe a girder truss as well. So that's one way of like orienting the truss. The other way is span now. If you span the roof truss this way, like the vestibule roof this way, then when you design the roof truss, if this is your roof truss, that one, and then it's either you use a beam or a girder truss, your load would be like that. So this is 70.18, and then this is 130.3. So you design your truss with this load, and then you size the like there will be a beam here, like at the main entrance, and then on this side, your beam here would be supporting the upper roof, and then you will have your girder truss here. And then the girder truss would be just you can just call out in your drawing, like say this one is pre-engineered roof trusses at say 24 inches on center, and then you have your pre-engineered girder truss. So when the truss manufacturers see that layout, then they will design it as a girder truss with this load. Now on your drawing, you have to show your snow drift diagram for them to. I mean, if you forget about it, they can size it. I mean, those truss manufacturer they know how to calculate, or if they have to consider snow drift. But it will be based on their um, analysis or assumption. So if it is not shown in the drawing, then what will happen is they will size the truss based on their assumed snow drift, and then you have to check the snow drift to make sure it is correct. So you better include that in your drawing. So when the truss manufacturers look at your drawing, they already know what the snow drift to consider. So another way of framing the vestibule is if you have, so this is your wall, and then this is your opening right here, 10-foot opening, and then you have your wall right there. So this is 15 feet, this is 20 feet. So we have another opening here, the main entrance. Another way of doing that one is you will span the truss in this direction. So you can do that. Now the only downside of this one is because our snow drift is like that one, then this truss, the load for this truss is different for this one. Unlike if you span the truss in this direction, then you only design one truss, or the manufacturer will only design one truss, and then they would apply that to all the vestibule trusses. But if you lay out your um, trusses this way, then this truss will be different, this truss will be different, this truss will be different, and this truss will be different. And usually, what they will do, because you will only have, I mean, most truss manufacturer will do it this way. They will design only one truss, and then they will just change the spacing according to the load. So they will only design, not design one truss, but there will be only one section, one truss profile. It will be similar. Like all of these trusses will be similar, and then they will adjust the spacing. So if this is your vestibule, so maybe these trusses are either double at 24 or 12 inches on center, and then as you go away like farther from the main wall, it will be 16 inches on center, and then 24 inches on center. So that's how I would say 99% um they will do it this way. They would make the truss spacing closer, and then just have one profile. Otherwise, they will have if they will have the truss here spacing at 24, maybe this truss you will have a bottom chord of 2 by 8 or 2 by 10 bottom chord, or and then this one will be 2 by 8 and the next truss will be 2 by 6, which is ridiculous. So what they will do is just have one single truss profile, and then they will just adjust the its spacing. So we will try designing the truss. What will be the beam section if we will span a beam. So if we will span the joist this way, and then we will design a separate beam to support the gear truss, just the beam supporting the vestibule truss. We will not apply the load from the roof because we have another header here for the opening. So we will design this truss and then this beam outside the wall. So that's how we will frame that one. So if we go forte, so forte web, so we already have, oh no, we haven't designed the roof truss, vestibule roof truss. So we will call it RT roof truss 01 or 02. So let's copy that one, and then this will be RT02. It's either you call it like snow, but we already know that snow governs on this one. So you can just leave it like that. RT02, it's no. And then this span is 15 feet, that one. And then we'll have out. So if the diagram or the beam is not showing the member, you just click this. I don't know if you can see it. This one here, this green one. Then it will show the member with all the support. Now, this one, although there will be a beam, but you will have on your framing, you will have a cripple stud because I mean, let me show you. Uh, so if this is our vestibule framing, so of course you will have a another opening here. Now, if you cut section, or if you detail the this is how I show the typical door opening detail. So you will have your in post, then you will have your in post here, and then you will have your beam right here. This is your beam, and then this is your cripple stud, the short stud, and then right here would be your three mirrors to support the header. So that's one way of framing the door opening. Another way is, instead of having the header right here, what you can do is this is your top plate, and then this is your in post, either double in post or single in post, but usually I will specify double in post. You can have your beam right below your header. Oh no, top plate. So this is your top plate, this one, and then you can have your header right below the top plate, and then you will have a like a door seal here, and then your cripple stud is basically right here below. So just the reverse of this um, framing here on your left. So this is another way. No, by the way, there should be a mirror as well here. That one, and then this is your door. If you have window, then you will just add window sill at the bottom. So these are so even if there's a beam, like if it's a window, unless it's a full height, unless it's a full height opening, then you will have your beam or your roof truss sits directly over the beam. But in this case, say if this is 10 feet, and then usually the door is only 7 feet, so you still have 36 inches um, of framing here, and then your beam is usually what 12, 11.78 or 14 inch if it's LVL or 2 by 12. So it's either you frame it this way or this way. Um, there are pros and cons on doing if you do framing like this one versus this one here. So going back to the girder truss, so this one, or not girder truss, the vestibule truss. So again, on your left or on your right, you will have a top plate. So this will be stud wall. Unless you have, like I said, unless you have a full height beam, a full height opening, and then you will have your beam right. It's either flush and then you will have a hanger or build like a drop down beam. But on the left side, we have a beam. So right here we will have a beam, and then say this is microlam LVL, and then say two ply at least. So that is 3.5. But that is not bearing. This is hanger. So it's either you use a face mount hanger, right? It's either you do it this way, like a beam, or you specify in your drawing, pull out girder truss, pre-engineered girder truss. So we'll just do it like as if this is a separate beam. So your loads, so this will be tapered, right? So this will be tapered, and then our load is the same. Did load is the same, right? Uh, what's that? No, the upper roof was I think 30. Now this is vestibule. Maybe the dead load is a little bit smaller, so we'll just say assume 20 PSF. So it's either you will separate the tapered, the snow load and the dead load, or you can have this one and then even if you pull out as tapered, but you'll just make the load the same, 20, it will still show this one here. It will still show like a flat one. And then for the snow, this is where you change the what we call this one, the intensity. So, oh no, this is tapered PLF. Now, our truss is 24 inches on center. So, therefore, this one is 40. So, this is times 2 because you have tributary width of 2. And then this one is 130.3 times 2 is 260.6. And then this one is 70.18. So 140.36. 140.36. And then the wind load is minus 35. Minus 35. This one is minus 35. So see, so this is your load diagram. So it's tapered, right? So product selection. So this is just like a mock-up of your truss because all we need is the reaction. So you will have say 2 by 12 24 and then C3 ply. So that is okay. So then we will design the beam. Now for the beam, so we already have beam 01, then we will have roof beam 02. So again, as I mentioned in previous video, like this is how I name the members, so it's not confusing when you link all the loads and the reaction. So this is RB02, and then the span is 20, right? That is 20, and then out to out, because that's the overall length of the, or overall width of the vestibule. Now, this is say 2 by 6, so this will be 5.5, and then 5.5. Now, this one we have stud wall. It's not Premier because this beam will be sitting on top of the top plate. So we will have stud wall, then stud wall. You only select trimmer if it's really a trimmer, like the beam sits directly on your um in post or built up post. So for example, if we draw a detail, so if your beam, say if this is your top plate, your double top plate, and then you have yours built up post here at the bottom. Now if the beam sits like that one, then you have to select the stud wall because it sits on top of the top plate. But if you detail it this way, you will have your beam, and then you will have your trimmers like that one, and then you will have your top plate. You will start your top plate right here, and then you will have another in post. So this one here, this is your, is it visible? Yeah, this is your built up post. So this is your built up post, and then this one would be your in post for your wall. So you can do it this way. Now, if you detail, you have to make sure that your design match with your detail. So if you detail it this way, then you design it this way as well. So you will have trimmer. But if you detail it this way, you will have your beam sits on top of the top plate. Then your support when you design the beam would be like this one. You will have a stud wall. So for the loads, we will delete this one here, and then we will link the vestibule roof truss, which is RT02. And then this time you will select which reaction because it's not symmetrical. Now we are designing the beam, so that is reaction 1, so right here. And then that would be a uniform PLF, and then the span is 0 to 20. And then that would be front side. So yeah, 20, the beam span. So that is your load. And then you go to the product selection, Marklam LVL 1178, say 2 ply. I will see if it works. So your moment is 227%. So that's really, the stress ratio is like really, really big. So what you can do is you go back to the product selection, and then you will select, say this is 20 inches. 20 inches LVL, and then say 3 ply. We'll see 3 ply. So that's already okay. And then bearing is 82, then moment is 58. So maybe we can try 16. So it failed in deflection. Now we'll check what deflection did we use. So this is the improved criteria. So we will use the code minimum, which is 240 over 180. And then you go back to the calculation. Now we are okay. So if your finishings are not critical, if the beam deflects or the truss deflects and the beam deflects, then you can just use the code minimum for the deflection criteria. and now it's all black now. There's no more red. So you can use 3-ply 16-inch LVL. So it's either you size a beam, or like I said, you can specify a gear the truss and let the truss manufacturer design it. Or like I said, also that you can span the joist in the opposite direction, right? So if you have your vestibule like that one, this is your wall, and then you will span the joist in that direction, or the truss in that direction. So maybe right here you have 12 inches on center, and then as you go away from the main building, you will have at 16 and then at 24. So it's up to you if you do it this way. But you just have to make sure that if this is your roof truss layout as shown on your roof framing, the truss designer or the truss manufacturer will also lay out their truss like this one. So that's really important. So we are done with the vestibule truss here, and then the beam. So like I said, you can either separate another beam here, and then separate your beam also um for the vestibule truss. So it's really up to you. So we will proceed with the design of the wall stud. So this is only vestibule, so most likely the height is maybe 8 feet or 12 feet or 10 feet. So what's critical is the full height wall. So if you remember our floor plan, so this here we have mezzanine, and then if this is platform framing, so in this area, this one, our stud wall is only, like, the height of the wall is only what 10, the height of the floor height of your mezzanine or second floor. So that's 10 feet. But on this side, this one, we have a full height stud, which is 18 feet. So if that's the case, we will see, you have options. So it's either in this area, you will have, say, 2 by 6 or 2 by 8, whatever is required. And then you will have a separate um, stud size on this wall, because it's like the height is shorter. And then most likely that would be the case, because the contractor would really try to save some money, because like 2 by 8 is way expensive than 2 by 6. So it's either you, like I said, it's either you design this as, say, 2 by 6, and then this one is 2 by 8. But we will try if 2 by 6 will work on this full height stud. So let's go back to Jabacos now. So we will have a stud wall. So right here, wall, and then stud is one. So this is wall stud, then full height. So it's usually better to design it like the worst case. So when I design a stud, I will always assume I will always use the or design first the worst case, and in this case that is the full height. So height and supports. So member in info, there is no special on your finishing, so you can have L over 180 for your um deflection criteria, that is flexible finish, and then height and supports. Then height is 18, and then double top plate, then single ply bottom plate, and then for the unbrace length, there we have sheeting, so we can use the wall sheeting nailing, which is 12 inches on center. And then for the loads, so you will use or you will link this one, the roof truss. So you have the roof truss, which is, this will be a point PLF, and then reaction one or support one, it doesn't matter because on this particular truss, the load is symmetrical, and then delete that one. So we have the uniform load. Now, on this lateral load, because you allow the program to design for the wind loading, right here we select a location Alberta Grand Prairie. But if you want to apply your own wind loading, you can check this one here. Do not apply wind load settings. I prefer to enter my own loads on the loads tab, right? So if your location is known, then just use the like apply the load, like let the software apply the load. And then if you prefer to input your own load for the wind load, remember this is not the same as the load you got from the primary structure, like the overall building. That's different. You have to use the load for your studs, and that is considering the tributary area. Now, going back to the wall stud, so this one, height supports 18, loads, we have this one, and then you already have you allow the software to calculate for the wind load based on your input, like the eave height or the stud height, like that, and then the location. And then product selection, we will use 2 by 6 at 16, and we'll see if this is okay. Now, with 2 by 6 at 16, it filled in compression as well as deflection and the interaction, because this is biaxial. You have your gravity load and then you have your wind load. So we'll see if we'll space the joy or the stud at 12 inches on center. Now it still failed in bending operation. So your other option would be upsize the stud. So next size would be 7 1/4, which is 2 by 8. This is the dimension number. So the drift size would be 7 1/4. And then 2 by 8 at 16 inches on center. Now this time, it is okay. So for the full height, you can use 2 by 8 at 16 inches on center, and then for sure, the shorter one, the mezzanine, the stud at the mezzanine area, that would be a 2 by 6. But we'll just check. So this is, we will copy that one, and then this is wool stud, not the full height, but the mezzanine area. So the only difference here is we have a height of 10 feet or maybe less, depending on your framing. If you go platform framing, then that's less than, we'll just say 9 feet. And then product selection, 2 by 6 at 16. Then see, it is overkill. But you cannot use, I mean, you can use 2 by 4 based on the criteria because you only have one roof and one floor. On the upper portion, you have one roof supporting one roof, and then on the lower portion, it's supporting one roof and one floor. Then 2 by 4 is okay unless it passes the design. But you can use 2 by 4 if you want. So this is 2 by 4. Ah, it failed. So your only option really is 2 by 6. And another thing also to consider, even if, for example, if the 2 by 4 passed in the calculation, you will have a like R value requirements for your wall. Then even sometimes even if it's only 2 by 6, 2 by 6 is fine. But it needs thicker insulation, then you have to specify a 2 by 8. It happens. Not always, but it happened in our project where the insulation required is thicker than what is required for the strength requirements of your stud. So we upsize the studs. So for the full height, you have a 2 by 8 at 16, and then the mezzanine area you have 2 by 6. So like I said, this wind load here in the report you can check like how much wind load was applied. This is 16.6. Now this since we are designing the individual stud itself, this is not the same as the load you get from Jabacos like this one here. If you go jabacos.com. So this is not the same load as this one here, primary structure figure 4. Because this wind load, you use this wind load for designing the overall the lateral frame lateral load resisting system. So if you design the shear wall, then you use this loading. But if you design the stud, the individual stud, then you use the tributary. Then there is a I will show you later. I have a in Jabacos there is no calculation for the individual stud. This one is for primary structure. Maybe in 2020 they will include that one. But the previous version of their online design tools, there is no provision or there is no soft program or section for stud design. So this is Grand Prairie, Alberta, and then Grand Prairie, the normal. This is I think we use rough. And then this is 6.1, and then this is 6.1 as well. So and then zero optional. So if you look at here, this is 2E. The worst case is for 1E is 0.35. So how much is 0.35 kPa? And then there is no, oh, this is negative to 0. So we don't have internal pressure, but we will apply the minimum, which is 5. And then PSF, then we will add that to 0.35. So we'll check how much is 0.35 kPa in PSF. 0.35 kPa in PSF. 0.35. So 7.3. And then you have your 5 PSF minimum, like code requirements for internal pressure. Then 7.3 plus 5 is 12.3. So that's only 12.3. That's why you cannot use this one. I mean, in the supplement for the National Building Code, there is a graph that you can use depending on the tributary area. So imagine this is 7.3 and then plus 5, that is 12.3, and then versus 16.1, right? So that would be critical if your uh, interaction here is, like say, 98% already, and then you are using the wind load from primary structure. Guaranteed that would fail. So you have to make sure that you are using the correct wind load. So this one is using 16.6. So we will see if we will get the same. Let me check. Um, so so we have this spreadsheet. So I created this one so that I can automate my calculation when I calculate for the girls for the stud. So the same Alberta, Grand Prairie, and then this is rough terrain in category one. So this is a always closed. And then building data, this is the longer dimension is 80, and then this is 60. Then the building eve height is 20 or 18, and then roof pitch is 0. Roof cladding composite. That's fine. Because we are only after the wind load. So we will go to say this one in wall column. Now our spacing is 16 inches on center, so that is 16 divided by 12, so that is 1.33 feet times the height, which is 18. 16. So 24 square feet, and then convert this into square meter, so divide by the squared. So this is 2.23. So this is 2.23 square meter. Mm, oh no, this is not in wall column because this is in wall column here. We will probably use the uh, wall girts. We can use the wall girts and we'll see. So I know this is because this one is pattern. I created this one when I calculated for the cranes building. That's why for tributary area for girls, it says here based on 10 square meter. So I think we can use we'll just use this one. So we have, or did we use category 2 on this one? If we use category 2, if we use category 2, how much is there an option there? 40? I can't remember that specified. Maybe they're using, we'll see what's the result um, if we use the category 2. Oh, it's right here. So if we use category 2, the wind load is 16.9, and then versus the in the 40 web, that is 16.6. So let's see, is there an option here to select category? So it says here seating wind load for tall walls, columns, and headers calculated in accordance with NBCC Division B Part 4, Clause 4.1.7. So this is the wind load provision. But it doesn't say here like what's the category. So it's only the same. It's almost the same if we use category 2, which is it is open but will be closed, like the structure will be closed in the event of a um wind like windstorm, something like that one. So maybe the default category for 40 is category 2. So for the wind load we have 16.9, and then so this already includes the external and the internal pressure. This one, uh, so this one here, CGCP plus CGI CPI right here. So this is your figure here for calculating the pressure, and then based on the tributary area. So the tributary area, as we go, like as the tributary increases, then the coefficient is getting smaller. So that's why for the whole structure, you where your area is really huge, then most likely you will use this full um, like 100 minimum or minimum here or maximum 100 square meter, and then you will have what, say 1.25, because 1.5 is right here, so maybe 1.25 cg cp. So that's why you have to be careful when you design for the, or when you consider the wind load. Make sure that it is correct, it is the correct wind load. So like I said, it's not the wind load that you get from the primary structure. The wind load for individual members, you have to account for the tributary width. So going back to 40, so we have, so for the full height, we have the stud 2 by 8 at 16 inches on center. Now, in our truss design, we already assume the stud to be 2 by 6, which is 5.5 bearing, then we are okay. Unless it's the opposite. Say we assume 2 by 8 in the bearing calculation, or the for the bearing when you design for the truss, and then the actual is 2 by 6, then you have to redo your truss. Let me double check. So our truss is the bearing, yeah, 5.5. So we assume a 2 by 6 stud wall. But in this case, if ever you assume this to be 2 by 8, then your stud, even if 2 by 6 is okay, then you have to use 2 by 8 stud just to meet the bearing requirements. Otherwise, you can use the 2 by 6, but you have to provide some kind of bearing enhancer. So if you look at Simpson strong tie, so now the contractor can decide which one is cheaper. It's either go with 2 by 8 stud, or you just buy a truss bearing enhancer. So uh, truss bearing enhancer. So this is what the truss bearing enhancer looks like. So it will help transfer the load uh, at the bottom, because or the side of the top plate. So in this case, this will be a shear instead of bearing. So this bearing enhancer has a capacity. Say each enhancer is 7.78. So each, and then you have, I don't know if this is pair or maybe each. So basically, you have how many trusses, and then you multiply it by 4, because you have two bearing enhancer at each end. So $7.78 times 4. So each truss is 31, but your stud is 16 versus 24. So you will times you will multiply this with 16 and divide by 24. So um I would say the equivalent price for this one, because the truss is at um 24, but your stud is 16. So to compare it with the price, that is $20. So you will spend $20 per stud. Now, I don't think the price difference between a 2 by 6 and 2 by 8 is $20 as well. I don't think so. So that's why it's cheaper to go just increase the studs, and it's even better for your insulation. You have more insulation. So, but if you have what we call this one, restriction with regards to the thickness. For example, if this is an addition, and then the existing is 2 by 8, for some reason it works 2 by 8 or 2 by 6, and then you're adding 2 by 8. So maybe the building was designed like many years ago, and 2 by 6 is fine based on the load combination. But on this one, this particular code, because you have that's the problem with upgrading like old building, because if you try to modify any member, then you have to analyze it with the latest code. So that's why most contractor will try to avoid modification on the structure. They can change the non-load bearing walls, and then they can redo the dry walls and repaint, but not modifying the structure itself, because that would trigger a full analysis of your structure, and most likely it will fail. So what else? We what? Oh, almost 1 hour now. So we will just end our discussion here, and then we will proceed or continue with diaphragm and shear wall in the next video. So bye mga lagan.